Okay, today we're interested in Gibbs free energy in the context of phase equilibria. So first of all, let's put that up. Alright, so today we're going to try to describe the energetics of pure substance phase equilibria. Well, first of all, we should try to pinpoint what that really actually means. So imagine you have some sort of system like this, a closed system, in particular isolated at constant temperature and constant pressure. Say for now that this region right here is some sort of vapor and this is some sort of liquid. For instance, this might be water. It's a pure substance system because we're only dealing with water, and it's a phase equilibrium problem because we have two different phases. We have a water vapor up here and we have liquid water down here. And we want to figure out energetically what is happening to allow these two phases to coexist. Why doesn't it go all the way to water as a liquid? Why doesn't it go all the way to water as a vapor? Okay, so what do we have in our toolbox that lets us attempt this problem? Well, we have our fundamentals of thermodynamics. So everything you should have learned previously in thermodynamics is what we'll use. In particular, that means our first two fundamental laws of thermodynamics. So we'll start with the first law. And remember, that just states that the internal energy can be written in terms of the heat to the system and the work done either to the system or by the system. So depending on the sign convention that you use, here I'm going to assume if the system gains heat, the heat term will be positive, and then if the system has work done on it by the surroundings, since it's getting energy, I'll call that positive work. The other fundamental we know is the second law of thermodynamics. So you'll notice here that this is a little bit different than what you'd expect. The second law will actually state that the small change in entropy is going to be equal to the reversible heat transferred to the system over the temperature. So what we've done here is we've used an inequality saying the entropy will be greater than or equal to heat over temperature. And here we're allowing irreversible processes in expanding the second law. So if it was a strict equality, we would have reversible heat, but since we're saying there's irreversible processes that we could model, we're saying that the heat isn't necessary to be reversible, and you have the chance that your entropy is going to be higher because of that. Okay, so we're going to start with these first two laws, and we're going to use a bunch of assumptions, and you'll see that it'll actually tell us something pretty profound about how systems behave under phase equilibrium conditions. So the first assumption that we will make is we're going to say there's a lot of work that could be done to the system, but we're saying that only PV work is going to be done by the system. So there's many other kinds of work you could have. You could have shaft work, you could have mechanical work, but we're saying the only work that is possible for the system to do right now is going to be compression-based work. So either expansion or compression of this to let this, I guess, piston go up or down. That's the only kind of work the system is allowed to do. So we'll sub that directly into our equation over here. So now this work term has become negative P dV. Okay, the other thing we're going to use is this trick here. So we're going to say, all right, nothing changes in the system if we just subtract absolutely nothing. All right, fair enough. What do we hope to accomplish by doing this? You'll see this trick several more times, but what we hope to accomplish is say, okay, that lets us sub this in. So what we're really saying is that 0 is equal to V dP. Why is that true? Well, one of our assumptions will be, as I've written over here in this picture, that if you're in phase equilibrium, then the temperature of the vapor, for instance, and the liquid down here must be the same, and the pressure of the vapor and the liquid must be the same. So you're assuming that you're in thermal equilibrium as far as temperature goes, and you're assuming that you are in equilibrium in regards to the mechanical things, so constant pressure. That means that our differentials in regards to P will be 0. That's why this is equivalent to this. They're both 0. And that's why our differentials in regards to temperature will also be 0. And you'll see that in a bit. Okay, so why do we care to add in this term over here? Well, what it allows us to do is it allows us to group these things together. Here you see P dV minus V dP. Okay, well, there's also a negative sign out here. What you should realize is, if you remember calculus, in particular Calc 1, this is basically your product rule. So remember, if you have the derivative of two things multiplied by each other, you're going to get P dV plus V dP. And because you have this negative sign out here, that's going to distribute over both of them. So now we have everything here, once again, in, well, terms of differentials. Okay, well, the next thing we're going to do is we're going to try to deal with this del Q right over here. So we're going to pop right over to our second law and rearrange this a bit so that we have the del Q right over here. And then we're going to rearrange this over here so that everything here is equal to del Q. So once we've isolated del Q over here, you should see something pretty fundamental showing up over here. Now, if you remember back to perhaps a previous semester of thermodynamics, you'll know that the internal energy plus the work due to compression or expansion is, well, because the derivative operator is linear, we can group these together and hopefully you'll see it even more clearly. You'll recognize this as your enthalpy. Okay, and here you see we have a bridge between the first law and the second law under these assumptions. Now, first of all, it's very easy to get distracted and forget about what these things in thermodynamics actually mean. So we'll see this a bit again, but I'd like to make the point that you should really remember intuitively what enthalpy is. Enthalpy is, this illustration shows rather comically, if you wanted to conjure a rabbit out of thin air, the total energy you would need was the internal energy of the rabbit, so that's all the interactions going on within the chemistry of the rabbit, or the atoms that consist of this rabbit. And since you're pulling this rabbit and you're placing it in space that was already there, you need to push the air molecules already out of the way. If you combined these two terms, the pushing of the air that you need to do and the energy that the rabbit already had, this gets you your total energy, which is your enthalpy. We'll revisit this in a bit. Okay, so let's bring this and this together. So we're combining our first and second laws of thermodynamics under these two equations, and the result will be this. So again, this del Q and this del Q, you're going to simply get TdF is greater than or equal to dH. Okay, and first thing we're going to do is rearrange it so that we have a 0 over here. Now, those of you who have discussed Gibbs energy already probably notice what's going to be happening over here. But we're going to use the same exact trick that we used up above. We're going to subtract nothing, because that doesn't change the algebra that's going on at all, and then we are going to do this. We're going to say that S dt is actually equal to 0 as well now, in the same way that we got this result from the fact that we're at constant pressure, or we're in mechanical equilibrium. We're also saying that we're at constant temperature. So this dt is going to make this expression right over here 0. So we're able to change them and get that for free. Once again, we're going to use that trick to make our product rule and capture both the T and the S, or the temperature and the entropy, under the same derivative operator. And then we're going to say that once again the derivative operator is linear. So we can group these together, and hopefully you remember what the definition of Gibbs energy is, because that's what we have just created here. So this is part 1 of our way. Remember, our goal at the end is describe the energetics of pure substance phase equilibria. We use the first and second laws, we combine them with a few assumptions over here, and we found that when you have two phases that are in equilibrium, they need to be in equilibrium in regards to their temperature, their pressure, and now we have this result, that the differential of the Gibbs energy at constant temperature and at constant pressure of this pure species must be 0 or negative. That's what we're working under right now. Okay, so we're not quite done yet. If you've worked with Gibbs energy before, hopefully you'll remember what it actually is. We're going to use that magician once again, and I should state that this is from Daniel Schroeder. Well, again, going back to that rabbit, you need to use the PV work to move the air out of the way, the internal energy of the actual rabbit when you're summoning it, and then the entropy can potentially help you in your goal to conjure this rabbit out of thin air. So your Gibbs energy is the difference between that total energy of just pushing everything away and summoning the rabbit, and the entropy, which actually can aid you in doing this. So it is seen as the actual free energy that you need to provide to get this to happen. So what Schroeder says here is that you don't need to provide all the energy to get the rabbit here, because the entropy does some of it for you. So you only need to supply the difference, which is the Gibbs energy. Okay, so what else do we need to understand about Gibbs energy to understand where we're going? Hopefully you remember something about chemical equilibrium, maybe from general chemistry, hopefully from general chemistry. So the one thing we usually care about when we're talking about Gibbs energy is what is a spontaneous process. If your Gibbs energy is negative, your process is said to be spontaneous. More specifically, if your change in Gibbs energy is negative. And Wikipedia says that this process can continue on by itself without the aid of energy supplied to drive it. What that really means is that, if you think about it, your Gibbs energy is a balance between your enthalpy and your entropy. And if your delta G, or your change in Gibbs energy, is negative, then you are either lowering your enthalpy or increasing your entropy, both which are favored when you're talking about the overall thermodynamics of the universe. You want to minimize your energy because that's stable, and you want to maximize your entropy because that's what the second law says must be happening. Your entropy of the universe is always increasing, so you're really balancing between your energy minimization and your entropy maximization. Now, in regards to equilibrium, this is sort of something that goes on when you talk about Le Chatelier's principle. If you have a reaction going and you supply a lot of reagent, what is the actual reaction do? Well, it tries to counterbalance it by creating more product. And there's a whole bunch of different things that the reaction will try to do in regards to Le Chatelier's principle to try and balance this. I'm going to bring up one other point that might seem a little irrelevant right now. That is the state postulate. So with the state postulate comes along with this Gibbs phase rule, where you have the degrees of freedom equals the number of components you have minus, I believe, the number of phases you have, and plus 2. So that's given here. Typically when you're dealing with a pure substance, we have one species here, so that's 1, and you have, well, 1 phase, and that gets you 2 degrees of freedom. What does that mean that you have 2 degrees of freedom? Well, when you're dealing with a pure substance in 1 phase, let me try and fit this diagram. This is a pressure-temperature diagram for a species such as water. If you're in the region with 2 degrees of freedom, then you have a pure species in 1 phase. So that's, say, if you're in the gas. What these 2 degrees of freedom is, it means you can move either in the temperature direction or the pressure direction, and you're still within the gas phase. You have 2 degrees of freedom to move freely within this region and still be in this region. Same thing if you're in a liquid. You have 1 species and you have 1 phase, so your degrees of freedom is 2. You could move 2-dimensionally throughout this space and still be in a liquid. Now, what if you're in phase equilibria? Well, then your degrees of freedom, you're going to have 1 chemical species, such as water, and you're going to have 2 phases, such as liquid and vapor, in equilibrium. That means your degrees of freedom, by this equation, by this Gibbs phase rule, means that you're going to have 1 degree of freedom. That means if you're in liquid-gas equilibria, you must move along this line. You only have 1 degree of freedom, so you can't move away from this line. Here you can see the self-correcting processes of equilibrium. If I'm on this line at, say, this point right here in the liquid-gas equilibrium, and I increase my pressure, what that means is that I've generated some liquid. And if I've generated some liquid, I have less gas. Well, what is that? Well, okay, let me try simpler. So I'm at this point, and I increase the temperature. By increasing the temperature, I've generated more gas. If I've generated more gas, and it's a closed system, I've increased the pressure. So if I do small deviations from the equilibria, it will tend back toward the equilibria. So I'm back on the line because I increased temperature, that made gas, and the increase in gas increased the pressure, and I'm back on this line. And you could keep on doing this until you run out of one of the phases, and then you're back in one of these 2 regions. Similarly over here, if I, as I was saying before, if I increase the pressure, I've created liquid. What that means is I've lost gas, and you're going to be once again tending back toward this line. That's the principle of dynamic equilibria. That's essentially what Le Chatelier's principle says. Okay, so why do we care about this in the context of this expression right here? What I'm saying is what we expect, our expectation is that we want dg to be 0 for phase equilibria. So again, if delta G or dg is negative, that implies there is some spontaneous process going on, that it has directionality. But when you're observing these 2 phases over here, such as a vapor and a liquid in equilibrium, what you're seeing is absolutely nothing happening. You are at the bottom of an energy well, which means you're in a system that you would expect to look like this, that keeps on tending back to equilibrium as long as the the perturbations to the system are small. In other words, what we want is we want no directionality. We want our Gibbs energy to be 0. And what we'll attempt to now is prove this. Prove that this expression should be equal to 0. So let's try that. I'm going to pull this down here. And now we need to rephrase our problem a little bit. Okay, so like before, let's get our little diagram out. And this time it'll be a little bit more complicated. So again, we have an isolated system at constant temperature and constant pressure, and here we're saying there's a phase. So phase alpha, some phase alpha. You could think of it as a vapor for now, but it could be a liquid, it could be a solid. Same thing here, we have phase beta. And we have some number of moles n, and they have their own intensive Gibbs energy. So really, Ng here represents the entire Gibbs energy that's present in this phase, and the entire Gibbs energy that's present in this phase. So in other words, the entire Gibbs energy of the system is given by this. So remember, this big G is an extensive Gibbs energy, and these smaller G's are intensive Gibbs energy. So this is Gibbs energy per mole, and this is Gibbs energy. And the N's are moles. So the entire Gibbs energy of the system is the sum of this and this, because the molecules here have some energy, and the molecules here have some energy. So if we include all the molecules, that's how much energy you're going to get. Okay, the next thing we want to do is we want to make this look similar to this. This is a differential, this isn't a differential, so we need to take the derivative of both sides. Okay, here we have a little bit of an issue. We could distribute that differential operator, and what you'll get is this. Why are there 4 terms? Well, you'll remember we need to use the product rule here, so this is a product and this is a product, so each of those will generate 2 different terms. Okay, why are these 0 then? So your dg alpha is 0 and your dg beta is 0. Why is that the case? Well, your Gibbs energy should be constant, because remember, your Gibbs energy is a function of the enthalpy and entropy of the system. And if you're at these working conditions and your Gibbs energy is intrinsic to whatever material you're using, then it should not be changing in regards to time. The intensive Gibbs energy. The overall Gibbs energy, the extensive Gibbs energy, is still possible to do this. So again, the justification is constant temperature and constant pressure means there's no change in the Gibbs energy of each of these phases here. So I'd say the liquid water's intensive Gibbs energy doesn't change, and the vapor Gibbs energy doesn't change. Okay, so now let's invoke what we had before. Our Gibbs energy is at most 0, and everything else is negative. So if we combine that here, we have this. So the survivors from that product rule expansion and their sum. Okay, now we could do one more step to make things a bit easier. If we have this dni or this dn, well, dn alpha or dn beta, what that means is you have moles transferring from one phase to another. Remember, if your moles are changing from alpha, you're either gaining moles in the alpha phase or you're losing moles in the alpha phase. And since we're in an isolated system, the material cannot be lost to the surroundings. So any transfer of moles that's happening must be happening between these two. In other words, if you're losing alpha, that means it's becoming beta. And if you're losing beta, it's becoming alpha. What that means is that these two differentials are equal and opposite. And what that allows you to do is distribute like so. So what you're left with is, if we make this substitution, is your change in Gibbs energy the difference of Gibbs energy between the two phases and the change in the number of moles. So really, at this point, we have three different scenarios. We have for this to be negative or equal, we could say this term will be negative and this one will be positive, or this term will be negative and this one will be positive, or they're zero. So let's start by making those assumptions. You'll see what I mean in a little bit if it's otherwise unclear. So our first assumption is, say that the Gibbs energy in the beta phase is greater than the Gibbs energy in the alpha phase. Okay, then if we want this expression to be negative, what we need is that this is negative. So we're saying that dn beta is negative. Okay, what are the implications of that? Well, it means if you have your system and it's like this is what's happening. Your dn beta is negative. What that means is you're losing moles from the beta phase. If you're losing moles from the beta phase, they're going to the alpha phase. The other thing you need to remember is, if your Gibbs energy is intensive, and you're saying that the Gibbs energy of beta is always greater than the Gibbs energy of alpha, and since this is intensive, it doesn't matter how much you have. So what it implies is that your overall equation here will be negative, and you'll completely convert from your beta phase to your alpha phase, and you'll be left with nothing but your alpha phase. Okay, what's our other situation? Well, our other situation is going to be the opposite. It's that our Gibbs energy in the beta is less than our Gibbs energy in the alpha. But if we want our overall expression to be negative, once again, what that means is that dn beta must be positive. What are the implications of that? The implications are that in your isolated system, if dnb is positive, then you're gaining more of this beta species. Well, more of the beta phase. The alpha is being converted into the beta, and at the end of the day, you're going to be left with nothing but beta. Okay, so as I was talking about before, in regards to the Gibbs energy, and what I was trying to stress so much was, this isn't what you see when you see chemical equilibrium. You see the bottom of the energy well. You see these two phases coexisting. You don't see it all being converted to vapor or all being converted to liquid. You see them remaining together for extended periods of time. What that means is that you're not seeing either of these two phenomena here. Well, what have we assumed here? We've assumed that this side of the equation is going to be less than zero. We've assumed this is going to be negative. And we've looked at both the cases where these can be negative. And we see that that doesn't fit the reality of the situation we're looking in. So what that forces us to conclude is that this shouldn't be a less than sign. This should be an equal sign. That reflects the reality of what we're dealing with here. In other words, we're saying that the Gibbs energy in this alpha phase must be equal to the Gibbs energy in the beta phase. Why? If it isn't, either of these scenarios happen, where one of the phases is completely converted into the other phase. What we're saying is chemical equilibrium happens because chemical equilibrium is the bottom of this energy well. It is the most stable state that these two different phases can coexist in. It's saying that at this point on the pressure temperature diagram, right here, the system doesn't want to be completely gas. It doesn't want to be completely liquid. It is actually thermodynamically more stable, more favorable, lower energy, higher entropy if it is a coexistence of the two phases. That is what it is saying. It's saying the Gibbs energies must be equal between the phases. Okay, so let's examine one more system to see if we could understand really what's happening here. So, say you have an isolated system, once again, at constant temperature and constant pressure, and you have a solid form of A and a gaseous form of A, and some gaseous B here that's not participating at all in what's happening. Really, you're interested in the phase equilibrium between this solid A and this vapor A. Okay, so the first assumption we're going to make is that the A that we're seeing is an ideal gas. What that means is that the internal energy of an ideal gas, if you remember, is only a function of temperature. It goes back to that kinetic molecular theory where you have just a bunch of billiard balls bouncing around all over the place. The only thing that affects the internal energy of that gas is temperature. Okay, so then if we're going to look at the internal energy as we see more and more of this A present in the vapor, we're going to see a linear profile. Why? Well, again, the only thing that affects the internal energy is the temperature. Well, the other thing that affects the energy of the system is how much of it is actually present. So if you have more and more gas in the system, remember gas has a higher internal energy than solids. So in the conversion of this solid A to gaseous A, we're saying the internal energy of a gas is higher than the internal energy of a solid. And that's, if you remember back to internal energy, it's all the sum of all those molecular forces, one of those being kinetic energy. Gases have much higher kinetic energies than solids. So I hope that convinces you that it makes sense for this to be linear for an ideal gas. And again, really understand what we're saying here is that as you vaporize, as you convert this crystal from a solid to a vapor, you will linearly increase the internal energy of the system, because the only thing that matters in the internal energy is the temperature of the gas. For the system, it's the conversion from one phase of low internal energy to a higher internal energy phase, so from solid to gas. Okay, how can we look at the entropy of this system? Well, what we'd expect is that it would look something like this. So again, the temperature is constant, so the only thing that's changing is you're converting your solid to a vapor, and you're saying that you'll get diminishing returns as you do this. What that means is that if you have all perfect crystal here and you vaporize a little bit of it to vapor, you get a pretty big increase in entropy because you're greatly increasing the degrees of freedom of your system. But as you vaporize more and more of this crystal, you're going to get diminishing returns in your entropy. As there's more and more vapor already present in here, adding a little bit of vapor to the system from the solid doesn't increase the degrees of freedom quite as much as it did initially. So it's going to tail off as you increase it. Okay, and if you remember, our Gibbs energy is a function of both the enthalpy here and the entropy term here, the entropy times the temperature over here. So if we're going to look at our Gibbs energy, it would look like this. So again, it's going to be this function minus this function, and that's what you're looking at down here. And what you're looking at is what I was telling you about earlier, is this sort of energy well you have here. You're really trying to optimize your interplay between enthalpy and your entropy. In other words, you want to tend toward the bottom of this energy well. What that means is that if you're particularly, remember this x-axis is how much of the A you have in the vapor. If you don't have a lot of the A in the vapor, it means you have a lot of it in the solid. If you have a lot of it in the solid, that means you have a pretty low enthalpy, which is favorable. That's good. Your internal energy is low because most of it's in the solid, but you don't have a lot of entropy, and you want to maximize your entropy. So what you're going to do is you're going to increase in the vapor until you're at the bottom of this well. So if you don't have a lot of vapor, you want to create more vapor because you want to increase your entropy. At the cost, you increase your energy a bit, but it's okay because the overall Gibbs energy of the system is still tending toward the change of zero. And again, the change of zero is when you're at that stable minimum and you don't want to move in either direction. And if you do move in either direction, you have this self-correcting dynamic equilibrium that's going to bring you back to your point of maximum stability. Likewise, if you're going to be high in vapor, if you're over here, then you have a lot of internal energy because you have a lot of molecules in the gaseous phase. So that high enthalpy, that high energy is not favorable. You want to minimize your energy. You already have a bunch of entropy because of the amount of gas you have. So you want to tend backward toward here. You want some of the vapor that's present here to deposit back into this crystal. So again, you want the right balance of both these phases. You don't want complete solid and you don't want complete vapor, because complete solid doesn't have enough entropy and complete vapor has too high of an enthalpy. So it's really this dynamic equilibrium, I'll keep saying that, between the two extremes that you actually find your true free energy minimization. Likewise, if you think about temperature, what's going on here? Well, if you're at a lower temperature, why do you prefer more solid? Well, remember there is this temperature factor over here in the entropy term. If you're at a low temperature, that means that your entropy term will be less important. That means your enthalpy term will be more important. Okay, remember, if you want to be at chemical equilibrium between these guys, you want to minimize your free energy. What that means here is that if your entropy is less important, your enthalpy is more important. You want to minimize your enthalpy. What has a lower enthalpy, a solid or a gas? Well, a solid does. So if you're at low temperature, you'll see solid preference over vapor preference. Likewise, if you're at a high temperature, and remember you're trying to minimize your Gibbs energy, it means that your entropy term over here is much more important. It means that your entropy term is perhaps even more important than your enthalpy term. So you want to try and maximize your entropy. What that means is that you look at the entropies of having more gas versus the entropy of having more solid, and you realize that gas has a higher entropy than solid, and if entropy is more important, you want to maximize that to get your lowest Gibbs energy, and thus, if the system is at a higher temperature, the gas state is preferred. Really try to understand in particular, well, first of all, this is super important, that the Gibbs energies of the phases are going to be equal. Understand that we came here from the first and second law under these assumptions. Understand what is really meant by enthalpy. Understand what is really meant by Gibbs energy. Understand what these degrees of freedom really mean on a phase diagram, and how you have that dynamic equilibrium at your phase regions. And understand this argument here, that this entire argument of this example here is that you want to minimize your Gibbs energy, and it's a balance between your enthalpy and your entropy and the phases that you have that prefer each of them. All right, hopefully that didn't confuse you too much. We'll try to do some problems next time.